Hello and welcome to the lecture video for Handout 1, covering a calculus supplement for the topics of kinematics and drag. Okay, so let's get into the basics here. All right, so in this first handout of this supplemental class, we want to talk about position, displacement, and velocity. Sort of a good grounding starting point of physics in general, but here of course we're going to take a calculus view of these topics. We want to recognize that acceleration is the derivative of velocity with respect to time. We want to recognize that velocity is the derivative of position with respect to time. We want to recognize that velocity is the antiderivative of acceleration integrated over time. Recognize that displacement is the antiderivative of velocity integrated over time. So you can see there's these derivatives and antiderivatives, and they all tie together these three, well, physical terms, physical quantities: position or displacement, velocity, and acceleration. Okay? All right, so that's the idea. So we have a couple of key calculus concepts here. I'm not going to cover the physics concepts since this is a supplemental class. You would have learned about the physics concepts in your main physics class. So these are just the calculus concepts that we need to review, assuming you've seen them in a calculus class, but we're just going to give you a little bit of review, a reminder, okay? So reminder number one, the polynomial rule of derivatives and antiderivatives, okay? So the idea is just this. If I have a function of the form some constant times x to the n power, then when I take its derivative, shown here in this derivative notation, so taking d over dx of f, then I'm going to get n times that constant times x to the n minus 1 power. Excuse me. So the idea is that this is the power reduced by 1, and whatever was the previous power gets pulled into the front. Okay? All right. So what about the difference between definite and indefinite integrals? Okay. Well, let's take a look here. So we have that a indefinite integral of this form here is going to give us the function. Notice this is the derivative, right? So there's that derivative notation. So if I take the integral of the derivative, then I get the original function. But that since this was an indefinite integral, there is no notation here on the actual integral symbol. So I get c, which is called a unknown constant of integration. Okay? A definite integral, on the other hand, gives this form where there are limits of integration, and so I don't have a constant because I just evaluate my function at the upper limit minus the lower limit. We'll tend to use the definite integral more as we actually solve problems that will involve integration in calculus. And if this idea of derivatives and antiderivatives doesn't sound as familiar, as it could, here's just a quick overview of those ideas. Okay. So first of all, in a sense of, well, graphing it, we have a function on the vertical axis. Here, this is just a function of x. Okay, just some function of x, a position function, really, right? Because on the horizontal axis we have x. Okay. And the idea here is then if we're going to take this function with integrate it with respect to x, then we're going to have this form here, right? We're going to have df over dx, and that is the tangent line. So conceptually, in terms of graphs, the derivative is a concept that represents the instantaneous slope of a tangent line of that curve. So the instantaneous slope at this particular point is this pink line. Okay, and that would be, say, at the point x2. On the other hand, the antiderivative represents the instantaneous accumulation of area under the curve. It's how much area has accumulated, at least in the case of a definite integral where there's definite limits, going from where you started, say at x1, here it kind of looks like 0, right? But wherever it may be, up to some final point x2, right? So that would be the integral, the area under the curve. And if you were to integrate to a further point, of course, you would have a greater or just different area, in this case, greater, okay? And then this right here is actually the idea of antiderivatives. It got moved down here, so I apologize for that. But this is just a quick reminder of the polynomial rule. So here I showed how to take derivatives with polynomials, right? Where we just put the power in front, and then we reduce the power by 1. When we're doing antiderivatives, we just essentially do the opposite. So if we consider a function of this form, so some constant times x to the n power, then if we're going to integrate this function, and this is going to be kind of an indefinite integral, but not one where we really care about the concept of integration, we just care about the rule for polynomials. So when I do it, notice what happens. So instead of pulling the n in front, like I did for the derivative, instead I divide by n plus 1. And then instead of reducing the power, so n minus 1, I raise the power. Okay? And this probably all sounds familiar. And the idea, of course, is that derivatives undo antiderivatives and antiderivatives undo derivatives. And if you look at these two rules, you can see that that idea exactly holds up. Okay? So how does this all relate to calculus? Well, here we go. We've got velocity. We see that velocity has a limit definition of the derivative. All right? So the official definition of velocity is the first time derivative of position or displacement. Okay? So we're not going to be integrating with respect to x. X here just was some general variable. Really, primarily what we do integrate or take derivatives with respect to is position. Oh, excuse me, is time. All right, is time. Now that's not to say there aren't some cases, but the majority of introductory physics, our functions are functions of time. Okay, and indeed that's what we're seeing here. Velocity is the first derivative of displacement with respect to time. Okay, well, what about acceleration? Well, acceleration, using the limit definition, is the first derivative of velocity with respect to time, or it's the second derivative of displacement with respect to time. Okay? So, this is just the second derivative notation. And if you're wondering where you put this squared symbol here, why is it in front of the d, but here it's in front of the t, is because essentially this is your operator here, this d squared over dt squared, and that says it's taking the second derivative of x. Okay? And that's where you'd actually put your variable. Okay, and then as far as the integral, we go down and can take a look at these two lines here. These are set up as what maybe would have been a definite integral on this side, sort of just, in other words, if I was to take dv and integrate it as a definite integral with respect to v, well, like this. So it would be dv and from v naught to v. Well, when I do that, notice what I get. I would then just get v minus v naught, right? Because it would just be the upper integral or the upper limit minus the lower limit. And that's ID here. This just represents the change in velocity. And the change in velocity is the integral of area. So in other words, or integral of acceleration, all right? This is not area, this is acceleration. Likewise, if I was to look at the change in position, it's the integral of velocity. So in other words, if I had an acceleration curve, a function that I graphed as a function of time, or I had a velocity curve that I had graphed as a function of time, the area under either of those curves would be either the change in velocity or the change in displacement, respectively. Okay, well, the change in position, which we call the displacement. Okay, so that's this. These ideas obviously are closely tied together because they're just derivatives and antiderivatives. In other words, integration. Okay. All right, so let's put it to practice with one simple example. Okay, so here's the example I'm going to show you. It kind of captures a lot of the ideas. Suppose that the x of velocity, so that's just v with the subscript x, of a car at any time t is given by this equation. Okay, so look at this equation here. Now this is the velocity equation for a car. Now we've seen velocity equations for cars when they are, say, constant acceleration. And in fact, I have a note here. We can use these definitions of velocity and acceleration and the relationship with derivatives and integrals to derive the kinematic equations. And remember, the kinematic equations is the name given to the set of equations for the common physical situation that involves constant acceleration. Why is it so common? Well, gravity is constant, at least if you don't change your height that much. And so it comes up a lot. It's an important physical situation, right? But sometimes you have accelerations that are non-constant. And if you have a non-constant acceleration, you're not going to have a linear velocity. For example, you might have a parabolic velocity. Okay, so what then would the acceleration function look like? Okay, well, that's going to be our first question. What is the acceleration of the car as a function of time if this is the given velocity function? Furthermore, what is the acceleration at a particular time, 5 seconds? Then, if we know that the car started at position 0, at time 0, then what is the displacement function of the car as a function of time? Okay? And then lastly, what is the displacement of the car at a specific velocity? So in other words, plugging in a particular time into the function that we're going to get from C. Okay? So let's see how we would approach this. We're obviously going to use integrals and derivatives. When do we use each? Well, since we're given velocity, if we want to get to acceleration, we have to take the derivative. Okay? So here we have that the acceleration in x, the same direction we're working in, it's a one-dimensional problem. Okay, but I still wanted to specify because you might see two-dimensional problems, and it's good to, to remember that this would just apply to one axis at a time. And so here we're just going to be taking the derivative of velocity, the x component of velocity with respect to time, okay? And so here it is, this is the derivative. I'll plug in the function, okay? And then I'm just going to follow the polynomial rule, okay? Well, if I follow the polynomial rule, then we can see here, and I really kind of wanted to work it out as a good reminder if you haven't seen the rule recently, is I would then I do t minus 1, okay? And then I'd multiply by 0, right? Because here, look, this is a constant. And that means that, the idea here is that this was t to the 0 power, which means the 0 goes in front, and then this becomes n minus 1, which would be negative 1, but it doesn't matter because you're multiplying by 0. And so the way that people always remember this is every time you take the derivative of a constant, because notice there's no function here, there's no t, which is our variable. Whenever you take a derivative of a constant, it's always 0. But it's also totally consistent with the polynomial rule, okay? And the idea here is I'm going to take the 2, put it in front, multiply by the coefficient that was already there, just the number, and then my t squared becomes just t, because I would have 2 minus 1 as the power, which of course is just 1 or just t, okay? Just linear. All right, well then look at, we have 2 times 0.5 in terms of the actual coefficient here. That means our acceleration just becomes 1 meter per second cubed. This is the coefficient. This would be the correct units of that coefficient, because if we multiply by seconds, then we'd have a second up here canceling off one of the seconds below, which will give us a second squared in the denominator, which is the units we need for acceleration, meters per second squared. And so this is a rather simple function for acceleration, but the fact that it's not constant, that it's a function at all, is something that we need calculus for, okay? That you wouldn't see in a class that didn't involve calculus and physics. And this is a real life situation. This would be acceleration that is gradually increasing. This is like not just pushing the gas pedal all the way down, but pushing it gradually more and more. So the car is accelerating, but also the acceleration is increasing. It's increasing at a constant steady rate. Okay? All right, and then we just wanted to evaluate at a particular time. That should be very easy considering it's such a simple function. We just plug in 5 seconds for t, and so that tells us that our acceleration after 5 seconds is just 5 meters per second squared. Okay, and indeed it has the units that we need for acceleration. Okay, in part C, now we're going to go the other way. We're going to go from velocity to position. And by what I mean by the other way is we're going to take antiderivatives. Okay, so here we just have basically that relationship between displacement and velocity. I've set up velocity as a definite integral, evaluating it from 0 to t. All right, and of course it's a function with respect to t, so the differential is dt. And then over here, instead of it being x minus x naught, it's just x. And here I'm using function notation to clearly show that x is a function of time. And the reason it's just x is because x naught is 0. How do I know it's 0? I was told in the problem. And you have to be, because whenever you take antiderivatives of kinematics, okay, right? Now, kinematics is a general term that applies to things that aren't just constant acceleration. Remember, kinematic equations is a name that's given to that specific set of equations that is the ones for constant acceleration. Okay, but anyway, so for kinematics, you have this idea that you need to know the initial conditions. If I don't know that the initial position was 0, then I can't ever actually have a precise function for position, because I don't really know how far I've gone if I don't know where I started. Okay? And that's the idea, that you always need more information when you take integrals than when you take derivatives. Okay? Because that makes sense, because you need to think about the graphical mean. One is the area under the curve. You only know that size of the area if you know where you started. But you can always get slope, right? Slope doesn't matter what happened before. So there's a fundamental difference there in terms of the information that is necessary in order to solve the different types of problems. Okay? But here we were told the initial position, so we can actually find the exact displacement, or initially just the displacement function. Okay? So now we're just going to go ahead and plug in our function for velocity, okay? And I go ahead and do that and then jump right ahead to actually doing the antiderivative. So I quickly change my integral notation to just the function notation, following all the appropriate rules. My 60 meters per second becomes 60 meters per second times t, because a constant just becomes linear when you do the antiderivative, because remember, what was a t0 becomes a t0 plus 1, which of course then is just t, okay? And then over here, I then follow the rule of putting a coefficient in front that is 1 over n plus 1, right? So that's where the 1/3 comes from. And then my t squared becomes a t cubed. Again, following just the rules for antiderivatives of polynomials. Okay? And so that's it. That's my function. But just clean it up a little bit by multiplying by 1/2 by 1/3, so it becomes a 1/6. Okay? Units check out. Okay? And so then in part D, I want to evaluate this at a particular time, but we weren't given the time. Instead, we were given the velocity. Well, that's fine. We have all the functions. We can plug this 100 into our velocity function, solve for t, and then plug the t back into our position function that we found in part C. All right? So let's go ahead and do that. Find t at which v equals 100. So there we go. We don't even have to use the quadratic formula because there's only there's only a t squared term. There's not a t term. So I just solve for t. I get 8.94 seconds. All right? That's just algebraically solving for t. All right? And then plug that in. Obviously, I'm only going to keep the positive solution because negative time doesn't make sense. Then plug in that particular time into this position function. And there we go, 660 meters. Okay? So that's the type of things you can do using calculus and kinematics. Okay? All right. So now let's move on to our second of two topics for this handout. All right. So these are this is the homework you're going to do. You're going to have 2 homework problems for this first topic, the topic of calculus and kinematics. Okay. So now on to the second topic, the drag force. Okay. Now the idea here isn't so much the force, but the form of the force. Because it turns out that this is a really natural combination of what we were just talking about. Because it's going to involve a lot of the same ideas. It's going to involve position functions, velocity functions, and acceleration functions. It's just going to involve them for things that aren't typical polynomials. Okay, because it turns out that the drag, Newton's second law dealing with the drag force and the way that the drag force relates to velocity ends up leading to natural logarithms, which means it also leads to exponentials. Okay, but let's show why, because it just happens completely naturally. Okay, but first of all, we want to make sure we know about how to integrate polynomials of power -1. And what do I mean by a polynomial of power -1? Well, I simply mean this. So this would just be a function that looks like this, just x to the -1, which is the same as saying that that's a function of x that is equal to 1 over x, right? Or something that has the form 1 over x. It doesn't have to be 1, right? It could be 5 over x, whatever, but it just has this form. Because if you think about it, if you follow those polynomial rules, it doesn't work, right? Because the power of x to the -1 is problematic for the polynomial rule, because think about what's going to happen. If I follow the antiderivative, then I have x to the -1, so my -1 would come in front, okay? And then I'd have an x to the 0. Well, actually, the 0 would come in front, right? Because think about what's going to happen, right? I'm going to have to divide by 0, okay? For the derivative, it's actually okay because the -1 comes in front, and then I reduce the power and it becomes -2, okay? So, so if I have f of x equals x to the -1, then f prime of x, so the derivative, is just going to be negative, let me write it one more time. So f of x equals x to the -1, so f prime of x is going to be negative x to the -2, because that's fine, I just reduced the power by 1. The problem is the other way, when you're doing antiderivatives, because then we're going to raise the power to 1, which is fine because it's x to the 0, but that means we have to then divide by a 0, and that does not work. All right, so it's it's not like the function just isn't defined. It's not as if there just isn't an antiderivative of this particular type of polynomial. It's that it ends up being something different. Okay, now I won't prove where it comes from, but it turns out that the resolution is that the antiderivative of x to the -1 is the natural log of x. Okay, that's where the natural log comes from. That's the whole idea. It was the mathematical resolution to this whole issue, historically speaking, in terms of mathematics. Okay, that's what the natural log is. It is the antiderivative of x to the -1, or in other words, the antiderivative of 1 over x. Okay, so graphically speaking, it looks like this, right? So this is a 1 over x curve, right? And if I then want to find like a shaded area like this, well, then it would just be it'd be equal to the natural log of x2 minus the natural log of x1. Okay, because I just evaluate the upper and lower limits. Right, so I just evaluate this function at both ones, right, both points. Okay, the upper point and the lower point, the upper limit and the lower limit. And an interesting thing then too is that if you recall your laws of logarithms, we can rewrite this as then there's the ratio. It's just the natural log of x2 over x1. Okay, which is pretty cool. All right, and there you go. That would be your area under the curve, which after all is the meaning, the graphical interpretation of the antiderivative, or in other words, the integral. Okay? All right, so why even talk about this? Why are we bringing up this particular calculus rule? Other than it is kind of a loose end with the idea that we presented before, the calculus idea. Because it's what happens with drag functions. Okay? How so? Well, let's look. Okay? Drag is really common. It's air resistance. So there's a lot of motivation to talk about this. It's a very real-life situation. But here we have a drag function. Notice, okay? This is the drag force. So F for force. Subscript here just means D. It has a particular form. It's negative b times v. Okay, so that's the drag force. B is just called the drag coefficient. It's something that would be given in the problem or that you could easily solve for. V is velocity. Okay, so what's the idea? The negative, by the way, is just the fact that it's an opposing force, kind of like the negative that shows up in Hooke's law, because it opposes the motion. Okay, but why is it BV? Well, because the idea is that the drag force is proportional to velocity. Now, it turns out actually there are a lot of drag forces for big things like cars, more realistically are proportional to velocity squared, but that mathematically is much harder to deal with. It can be solved for, but it's beyond, it's beyond the scope of an introductory class and involves introductory physics. So we just deal with the simple linear case. But it's still not, it's simple, but it involves logarithms and exponents. So, but still, why would the drag force even be proportional to velocity in the first place? Well, the reasons are a little bit, like, oh, it has to do with the way the molecules move, and there's just kind of this, kind of general argument. But first of all, it does at least intuitively make sense, because the idea is the faster you're going, the more drag you experience. People talk about that in terms of like mileage efficiency. How many gallons per mile you get. And when you drive your car faster, you get much worse efficiency on your engine. That's because the drag force goes up. Okay. It just, it becomes harder and harder to push through the air because you're forcing the molecules to move out of the way faster. So the drag force is proportional to velocity. Okay? And that's different than, say, friction, the other non-conservative or dissipative force. Friction is just all about, the substances, and that's it. Okay? At least a simplified model of friction. But there's no way to model drag without considering the fact that it really is proportional to velocity. And that's why you have something that you've probably heard before, the idea of terminal velocity. Okay? Well, that's right here. This is terminal velocity. Okay? V sub t is terminal velocity. Let me label it terminal velocity. Because what happens is, since the drag force is proportional to velocity, the faster you go, the bigger the drag force grows, until eventually the drag force grows so big that you stop accelerating. That's why you reach a final speed, because eventually the drag force equals the gravitational force, and that falling object has reached equilibrium. It's falling fast, but it's not going to accelerate anymore. Okay? And that's like a skydiver. They reach a certain speed and they stop speeding up. That's terminal velocity. And that's only possible because the drag force is proportional to velocity. Okay? So a little bit of physics there. Okay? Now, there's also a particular term called the time constant, which is really just a convenience. It's represented by the Greek letter tau, and it's just equal to m over b. Okay? And we can see here, right, because we see that the terminal velocity is m times g over b. B, again, is just the drag coefficient, which is just given in the problem. The units of the drag coefficient are mass per second, kilogram per second, okay? So mass per time. So then the the time constant is just the mass over the drag coefficient, okay? And the units of the drag constant are just time, okay? And it just kind of represents like if you have a large drag coefficient, that means that your terminal velocity is going to be large because it takes a long time to speed up. If you have a very small time constant, then your terminal velocity is going to be low because it doesn't take much time to reach that final state of falling. Okay, because that's kind of what we want to think about here, like a skydiver, something falling under the influence of gravity and then experiencing drag in the upward direction, kind of like this picture. All right, this is the if you think about it, pretty simple free body diagram for drag. There's just an upward force and there's a downward force. The upward force is drag, the downward force is gravity. Drag opposes the motion, gravity just is gravity. It just acts because of universal gravity, okay? So let's run through, because these are going to be our acceleration, velocity, and position functions, all right? And notice we list them in this order because they get increasingly complex, okay? But let's show where they come from. I want to motivate this real fast, okay? So let's first of all just do the Newton's second law, the net force equation for this simple free body diagram. Okay, so there's two forces, gravitational force, drag force equals ma. I've defined positive y as downwards. That's why a is positive and gravity is positive. Drag is only negative force. Okay, all right, so pretty straightforward, right? Well, then we'll just rewrite the gravitational force as mg. We'll rewrite drag as negative bv. The negative is already accounted for, so I don't want to double count it. And I got ma. Okay, that's fine. That's great. Now, what are we going to do with it? Well, we're actually going to solve for v. How are we going to do that? Okay, so this is neat. We rewrite acceleration with its derivative definition. Acceleration is the first derivative of velocity with respect to time. Okay, so now look at this. Now I've got a dv dt and a v. So in other words, I have a function and the derivative of that function in the same equation. Technically, that's called a differential equation. But this is a differential equation we can solve for easily by just grouping together our variables with our differentials, okay? So I want my v and my dv to be on the same side because then I can integrate it. And I want my dt to be, well, on the other side, okay? So how do I do that? Just some algebra. I just start moving things around. I'm going to zoom in a bit here. So all I do here is I'm going to, let's see. So I'm going to kind of take, I'm going to get v by itself because I don't want a coefficient in front of v. So I'm going to divide all the terms by b, which means my mg becomes mg over b. That looks familiar. That's terminal velocity. That's going to come up. And then my m over here just becomes m over b because, again, I just divided everything by b, okay? And I know to do that because I know that's going to kind of save me some trouble and when I actually get to the derivative, or, well, the antiderivative, okay? And then what I'm going to do is I'm going to multiply both sides by dt. Why do I want to do that? Well, because I want the dv by itself, and I want the dt by itself. Are you allowed to do that with derivatives? Absolutely. It's just called separation of the differentials, okay? Okay, so then what I want to do is I want to get this expression here that has a v in it on the same side as the differential dv, which means I'm going to divide both sides by this whole business inside the parentheses, okay? And then I'm also going to cross multiply both sides by m over b, which will become b over m, okay? So there we go. We got it done. We've got everything that is a function of v on the same side as dv, and everything that's not a function of v on the side of dt. Now, if we had things that were a function of t, I'd want them on the same, in other words, if I had a t itself, the variable t, I want to make sure that was on the same side as dt, but I don't. So these are just constants, in reference to this, this differential. Because look what I do in the next step. I just integrate both sides. Because I can completely do that. That is entirely allowed. Now that I have a dt, I can integrate, and notice I do a definite integral from 0 to t. And then on this side with the dv, I just integrate from 0 to v. Okay? So as long as I integrate both sides, I'm not breaking any rules of mathematics. Okay? So then what do? Well, now I just evaluate those integrals. This side, the left side, is very easy to deal with because this is just a constant, so it's just going to pick up a t. Okay? Because it's, when you take the antiderivative of a constant, it just becomes linear. Okay, but what about this side? Well, think about it. This side over here was essentially a whole function to the negative 1 power. So that means when I do my polynomial rule, then I have to then, well, turn my negative 1 into a natural log. It's just this rule. That's all it is. Okay? Now it might look a bit different because it's not the variable by itself. It's got, this whole second thing going on. Well, we don't have to worry about that because that's just a constant. And we also don't have to worry about something called the chain rule, which we'll talk about later in more depth, because there's nothing attached to the v. The v is just by itself, which is kind of the advantage of making sure that it was by itself. Okay? Now here is something though. Since this is a natural log, and unlike with when I'm doing a antiderivative of a polynomial, and I say, oh, I evaluate at t, because notice here my upper limit is actually the variable t, and my lower limit is 0. So if I multiply, so if I evaluate t, the variable, and I enter t, well, t evaluated at t is just t evaluated at 0 is 0. So it just becomes a single term. But with natural logs, if you evaluate them at 0, they're not, it's not going to become, it's not going to become 0 because there's two terms inside the natural log. So when I evaluate the lower limit, my v becomes 0, but I'm still left with a negative mg over b, okay? And that's important because that's going to, kind of shape our final solution. Okay, well, we got to clean this up a bit because there's a lot going on here. So I'm going to use the law of logarithms to take subtraction outside the log as division inside the log. Okay, and then we'll clean this up further. How am I going to do that? I'm going to raise both sides to the power of e. Why would I do such a thing? Well, because that gets rid of the natural log. And that means that over here, this just becomes an exponential. Specifically, it becomes an exponential to the negative b over m times t, which is an exponential decay. So in other words, this right here is as t becomes larger and larger and larger, is going to decay to what? 0. Okay? So as t approaches infinity, this whole expression goes to 0. Because of course it does, right? It is decaying to 0. Okay? And then I'm just going to isolate my v, which you'll see here. All right? And it's going to become that expression. How come? Well, because once I cross multiply and I solve for v, right? Because imagine just kind of multiplying both sides by this. All right, well then my terminal velocity then, by definition, is mb times g, Why? Well, I'll justify that in a second. And then remember, just simply to simplify things, I'm gonna rewrite m over b as tau, just to make the expression cleaner. Okay? When I do that, this is what my velocity becomes. In other words, all I did was just solve for that v, and there it is. Okay? Now think about why I'm calling this terminal velocity. What happens for really big t? Well, as t goes to infinity, this whole term here goes to 0, which means that v approaches, for large values of t, it approaches this thing in front, which of course is just m over b times g. And it has units of meters per second. That is what we call terminal velocity, which is a totally appropriate name for it. Okay? It's just the term, it's the final velocity. It's the final velocity once the drag force reaches equilibrium with the gravitational force. Okay? So this is where it comes from. This is where this drag function comes from. All right? And it's telling us that essentially the terminal velocity is asymptotically approaching a final velocity. All right? So, or the instantaneous vertical velocity is asymptotically approaching a final velocity, a final value. If I was to graph it, it would look something like this. Right? So this is Vy, this is t. It kind of come up and then it would level off. And it would level off at a value of Vt. Okay? Now, what if I wanted the acceleration as a function of time? Well, I could then, now that I have the velocity function, which I got from Newton's second law, then I can simply take its derivative. It's pretty easy to take the derivative of exponentials because when you take their derivative, they don't change. And so if I do that, if I take its derivative and I again get back to acceleration, I find that acceleration is just an exponential. There's no second term. This one has two terms, obviously, if I was to distribute the Vt. Okay? And that makes sense because essentially what's happened, that tells me that the acceleration is decaying to 0. Right? So if I was to graph acceleration as a function of time, it would just look like this. It would just start at g, because the initial value is g, and it would just decay down exponentially to 0. It would never reach there because it's exponential decay, but it would just get closer and closer to 0. Right? The acceleration gradually disappears. All right, and then if I wanted to integrate it a second time, which would require a bunch more of this business, then I could actually get the position function. It's totally doable. It's totally within the same exact rules that we followed. It's just a little painstaking to follow all the rules, and then you get, it has 3 terms. All right, actually I would have, because I distribute that in, that would be 2. Yeah, I would have 3 terms. Okay, and what it tells me essentially is that the position function approaches linearity, because eventually the velocity becomes constant. And once the velocity becomes constant, then the displacement would be linear. So it's not like the approaching a constant. It is basically an exponential function that is approaching linearity. Okay, so if I was to do a similar sketch here, it would look something like this. This would be y, this would be t. So at first it's like growing, it's curved, but then it kind of reaches a point where it becomes linear. See? And so that's actually what this function looks like. It's an exponential approach towards linearity, which is a little bit harder to wrap your head around other than the first two. Okay, the velocity and acceleration functions. Okay, let's do one example. Actually put this into practice. Okay, so by the way, this function does apply in a real life sense, the one that just has this BV form to small objects. It's called Stokes drag, that's the term for it, if you want to use a keyword search. And it applies to things like raindrops pretty well, kind of like small aerosols, pollen grains, those sort of things. It doesn't really apply to skydivers. In that case, it would have to be v squared, have to be proportional to v squared. Although we can cheat and call, come up with problems and just say, oh, we'll treat it as linear drag. Okay, but here we'll use a raindrop, which is a good real life application of it. So same force diagram, all right, drag, and gravity. That's it. All right, so it's the same one from the derivation before. In this particular example, since I already have the functions, I could just use them, okay? But I kind of rederive them within this example, okay? So I'll move through it at a decent clip because we've already seen a lot of it. So we're just going to use the drag function equals BV, all right? That's the magnitude of the drag force. All right, so then we just set up a net force in y. In this case, I'm defining positive y as up, so my net force equation is slightly different. This is good for comparison, so you don't get confused with the negatives. All right, and then I plug in the definition of drag, gravity, acceleration, and then I just go through the same steps. I'm going to then use the derivative definition of acceleration. All right, and then I'll do the whole business where I'm going to move my differentials around. You can see I'm setting it up in a really similar way. All right, and I've isolated my v. All right, and I got my dt and dv on different sides. All right, and then I want the variable by itself for the easier antiderivative. Okay. Justifying the step that you saw before. Then I'm going to do the integral of both sides, definite integrals. All right, and this is all, basically the same stuff we've seen before. Here I actually show them evaluating the limit at the upper and lower limits, which is why we get the subtraction or the difference of natural logs. All right, there we go. The law of logarithms. All right, now we're going to raise both sides to the power of e in order to get rid of that logarithm. All right, as I've done here. And here, look, I'm actually showing e to the natural log, e to the natural log. That'll just cancel out. Okay. All right, so then you just get the expression inside the natural log, okay, because I'm undoing the function, okay. All right, and then continue to clean it up, and this is again like the derivation before, and there we go. We've isolated v. All right. Here I'm not using the expression tau. I just left it as b over m, right? But this would actually, so m over b is tau, so that's why this becomes t over tau, specifically negative t over tau. All right, but you can write that exponent either way. All right, and then what was I asked for in part A? Well, I just asked for the velocity after 10 seconds. Well, now that I have my velocity function, okay, which I've again derived twice, right, just to kind of show it to you, I just plug in t, right? It's as simple as that. I just plug in t equals 10. Okay, there's the 10 seconds, and I plug in all the other values that were given because we were given a value of b, we were given a value of m. What else? We were given gravity. Okay, so then it's simply a matter of plugging in t equals 10 seconds, and there we go. There is our velocity. Okay. So, and then in part B, what fraction is this velocity of the terminal speed? Okay, well that should be easy enough, right? So I'm just going to note that the terminal speed, which I just set up here. So here, the terminal speed, after all, is once the acceleration is gone. So we could actually derive the terminal speed if we forget its form. We could just set up the Newton's second law, set it equal to 0 instead of ma, because a is 0. Okay, and then just solve for v, call that terminal speed, and then it becomes mg over b. So if you ever forget the terminal speed, you can quickly solve for it by just setting up a net force equation and setting it equal to 0. All right, so then my terminal speed is 544. Okay, well there you go. So then I just want a fraction. So I just want v after 10 seconds relative to terminal speed, and that tells me that this value after 10 seconds is about 16.5% of terminal speed. So that means it would take a while to get closer. If I wanted to get to say 99% of terminal speed, it'd probably take up more time, but it wouldn't be 10 times as much time, or even even 5 times as much time, because after all, it is exponential growth of velocity. It is exponentially approaching the terminal speed. Okay, just like the acceleration is exponentially decaying to 0. Okay, and then finally, I'm asked a position question. How much time does it take for the raindrop to fall 325 meters? So this is kind of an interesting one. This is probably the trickiest question you could ask involving drag functions and drag type problems. Because here I'm just going to use the actual form of the position function. All right. Do notice here that I was using k instead of b. I forgot to change that. So all the b's, all the k's should be b's. After all, it's just a variable, or just a constant for drag, and sometimes it is expressed as k, but obviously I want to be consistent and express it as b. All right. But here is just the expression for position as a function of time. And so then if I have a particular time, in this case 325, then I just want to solve for t. Now that is a tricky function to solve for. You actually can't do it algebraically, because you got a t up here in the exponent, and you've also just got a linear t out here. The only way to do it is to graph it, or to plug it into like a math solver, like Wolfram Alpha, or a graphing calculator that has a built-in computer algebra system like the TI Inspire. And then it will give you the value. And it turns out if you solve it with a calculator, or look it up online, Wolfram Alpha, or just graph it, that's always a good way to do it, we find that it's 8.34 seconds. Okay? So that's how long it takes to go that particular distance. All right? Now, an easier thing is to say how far have you gone after a particular time, because then you can just plug it in. Okay? All right, so that's what drag equations, or drag type problems look like. You have one for homework. It doesn't involve the position one, don't worry. It just basically you're just going to be looking at all you're going to be doing is looking at the velocity function. Okay, so hopefully this has been a good introduction to kinematics, and then a specific subset of kinematics, which is drag motion. Thank you so much for watching, and I look forward to discussing these topics further.